Hello there, this is Mo Hasanovic from Indian River State College and LASER-TEC Center for Laser and Fiber Optics Education. Welcome to our Introduction to Photonics video series. This is going to be our first out of 8 lectures. The title of this lecture is Nature and Basic Properties of Light. What we are going to talk about today, we are going to define the basic properties of light, such as wavelength, frequency, and period. We are going to talk a little bit about the dual nature of light. We are going to describe electromagnetic spectrum and sketch a diagram of its main optical regions. And then at the end of this lecture, we are going to talk a little bit about electromagnetic waves and their properties, and finally define the index of refraction. Since this is our first course in photonics, the first question that we must address is what the photonics is. We understand photonics as a field of science that has everything to do with the light energy, meaning generation, manipulation, transportation, detection, and finally use of light energy. Photonics can be found in many fields, in many aspects of our life, to the point that it is considered an enabling technology that basically helps many other fields of science prosper and develop. Light is present in almost every aspect of our life, to the point where we are very often not aware of its daily uses. So we can find it in our CD players, where laser light reflects off of a CD and transforms the returning signal into the music. We can find lasers and light in our grocery stores at the cashiers, where laser beams are reading barcodes. We can find laser in laser printers that are recording images on the paper. We can find lasers and light in the field of fiber optics, where we are transporting a huge amounts of data over so-called fiber optic cables. We can find light and lasers and photonics in the field of medicine, where we're performing different types of surgeries, including eye surgeries, popular as LASIK surgeries. Light is also present in the military field, where certain laser weapons are being developed, etc., etc. So basically, we are born with the light, and we are experiencing light on a daily basis from our first day of birth all the way until the end of our life. And we are basically, we cannot imagine our life without having a light. So obviously the importance of light is extremely important, and that also translates to importance of this specific field of photonics that we are talking about, and that is the main topic of this course. Now that we defined what the photonics is, the next question that we have to talk about is how to understand light and how to describe light. This question has been puzzling scientists and humankind for many centuries. Today, the definition that is broadly accepted is that the light is a form of electromagnetic energy that has dual properties. There are certain phenomena of light that can be explained only if you look at the light as a wave, while other phenomena that pertain to light can be explained only if you look at the light as a particle. So when we are dealing with the light, we are dealing basically with a so-called dual nature of light, where we are looking at the light as both a wave and a particle, and then also as a form of electromagnetic energy. So for example, when the light travels through space and passes through small openings, or when it moves from one medium into another, it is going to refract or bend. It is also going to reflect. So it is going to behave like a wave that's made up of many connected so-called electric and magnetic fields that are vibrating and traveling together both in space and time. On the other side, if we are looking at some other phenomena, such as absorption of light as it moves or propagates through a specific material, if we are talking about emission of light, those types of phenomena can be only explained if you're looking at the light as a particle. In order to properly describe light, we have to establish the language of light. We have to establish the terminology that we are going to use in the field of photonics. So the slide that is in front of you shows different types of quantities that we are going to use that are in a sense a language of light. So using these terms that are listed on this slide is gonna help us better understand light and better describe its properties. So we are going to talk and define each of these different quantities such as wavelength, frequency, period, amplitude, speed, phase, finally coherence, polarization, and energy. All these terms are extremely important. We are trying to establish the foundation of knowledge in the area of photonics. Without fully understanding these terms, it's going to be very difficult to be employed or to deal with different phenomena that relate to the light, and to basically build a career as a photonic or a fiber optic or laser technician. The first quantity that we want to define and describe is the term wavelength. Before we talk about wavelength, however, we want to address the concept of a wave. We said that light has a dual nature. It behaves both as a wave and as a particle. So what do we mean by a wave? How would we describe in simple terms what the wave is? There seems to be a certain analogy that can be established between different types of waves that surround us. So light as an electromagnetic wave is just one type of a wave. We also are very familiar with sound waves. And even if you're looking at the ocean, you can see ocean waves. So how would we describe a wave behavior? So when you talk about a wave, we are talking about certain repetitive behavior of a specific quantity, be it water or air molecules in the case of a sound wave. And we see this vibration or repetitive behavior where a specific quantity is basically undergoing through maxima and minima, through crests and valleys. So for example, if you're looking at the ocean wave, you'll see these crests and valleys that are basically distributed along the space, right? So at different locations you have a crest of the wave, at the other location you have a valley of the wave, and they repeat. So there is a repetitive behavior, there is this vibrating behavior that's being distributed across the space. But that's just one aspect of the wave. You also, in order to have a wave, you also have to have repetitive behavior in the time domain. So for example, if you're looking at the ocean wave, and let's say you are anchored in a boat on a wavy surface, a water surface, you're also going to be moving up and down. So in a specific time instance, you're going to be up on the crest of the wave, and after a certain time you're going to go down into the valley, and then again you're going to go up on the crest of a wave. So this repetitive behavior is now happening in time. So in order to have a wave, you have to have repetitive behavior or vibration both in space and time. Those two aspects are of vibration both in space and time is what characterizes any kind of wave. Now, based on what vibrates, you can have an ocean wave if you have a water vibrating. If you have air molecules vibrating, you have a sound wave. And specifically in our case, if you have a electric field and magnetic field vibrating, we are talking about so-called electromagnetic wave or light. So what you see on this slide is a geometrical representation of this repetitive behavior or vibration across the distance. So you can see that here along the x-axis we are basically representing the distance, and we see that at different points we have a crest of the wave, and then we also have a valley of the wave. In other words, we have a maxima and a minima. Wavelength is defined as the distance between the two neighboring crests, as it's represented on this specific picture. So we are talking about, once more, the vertical distance that's measured from the equilibrium position at any point along the wave. Very often we also define a wavelength as the distance over which the wave repeats itself. So if you measure the distance between the two crests of the wave, you are going to get the wavelength. So wavelength is going to be represented by the Greek letter lambda, and it's going to be measured in units of length, be it inches or meters, and then also some other units such as millimeters, nanometers, etc. On the other side, if we switch to the time domain and look at this repetitive behavior or vibration over time, then we are getting a different type of a plot, such as the one that's shown on this slide. As you can see here, along the x-axis, we don't have distance anymore. Now we are talking about the time domain, where along the x-axis time is represented. And as you can see on this slide, on this plot, you also have a repetitive behavior that's shown as this sinusoidal curve, where after some time, we are going up on the crest of the wave, and then we are going down into the minimum of the wave after some time, and then again up to the peak of the wave, and then down to the negative peak of the wave, etc. So it's just that in this case, all the repetitive vibrational behavior is taking place in time. We are defining the period as the interval of time over which the wave repeats itself. So if you want to measure the time from the one positive peak to the next positive peak, you are going to get the period. Obviously, period is represented in terms of units of time, seconds. We also define another important quantity, so-called frequency, that basically represents how many times you are undergoing through the positive peak or the crest of the wave in 1 second. So once more, frequency is defined as how many times or the number of cycles of the wave in 1 second. We are going to use the Greek letter nu. That's kind of like this curvy letter V that we are going to use to describe the frequency. And finally, we also have a speed of a wave, or in this case, speed of light, that is equal to 3 times 10 to the 8 meters per second in vacuum. So the speed of light in vacuum is a constant. And there is also a certain correlation that exists between the speed of light and its wavelength and its frequency. So there is 3 formulas that are shown here on the right hand side that correlate these 3 important quantities that pertain to light. So the speed of light, the wavelength, and the frequency are described by the equation C is equal to lambda times nu, and then also its derivations that are also shown on this slide. So to summarize, the light represents a form of electromagnetic energy that has a wavy behavior. We are using the term electromagnetic wave. So we are talking about the disturbance that takes place both in space and in time, and through this form of electromagnetic energy that has a wave behavior, we also have a transfer of energy or propagation of energy. We are talking about the disturbance in space that's been represented by the upper plot. Thus we have a distance along the x-axis, and on the bottom plot we are representing a disturbance in time. Thus we have a time along the x-axis. Another important quantity to be defined is amplitude. Amplitude represents the distance from the reference or zero line to the positive peak of the wave. So the light represents a specific type of electromagnetic wave that's visible to our eye. Light waves travel in straight lines, similar to other types of electromagnetic waves, including so-called microwave electromagnetic waves, waves at slightly lower frequencies compared to the light. The speed of light is approximately 3 times 10 to the 8 meters per second, or 300 million meters per second, or about 186,000 miles per second in free space. So we are going to see that speed of light is going to change in different media. For now we are talking about air or vacuum. So again, the speed of light is a constant that's equal to 300 million meters per second in air or vacuum. This slide briefly presents the units that are going to be used in photonics for some of the quantities that we previously introduced. So for wavelength we are going to use units of length, specifically nanometers and micrometers. For the unit of frequency we are going to use megahertz, gigahertz, and terahertz. And finally, for a period we are going to use units of time, specifically microseconds and nanoseconds. The table that you see on this slide also briefly presents some of different prefixes that we are using when we are expressing different units that are used to measure quantities of photonics. Now that we introduced the concept of a wave, we also want to talk a little bit about electromagnetic waves. Light is a phenomenon that's related to the electromagnetic wave behavior. So we want to look a little bit into the nature of electromagnetic waves. So when we're talking about light, or in general electromagnetic wave, what basically vibrates in this type of wave behavior are two quantities: electric field and magnetic field. These two terms are to a certain extent abstract because they cannot be measured directly, but there is a direct correlation between two other quantities that we are using in electrical engineering or in general in electricity. Namely, electric field is directly related to the voltage, while magnetic field is directly related to the current. So there are certain formulas, or if you wish, so-called Maxwell's equations, that are relating the voltage to the electric field. There's a law called Gauss law that basically correlates or establishes direct proportional relationship between the voltage on one side and the electric field on the other side. And then similar applies for the quantity of current and magnetic field. So what's important to remember here is that in the case of electromagnetic wave is the quantities of electric field and magnetic field that vibrate and show the wave behavior, and that the electric field can be directly related to the voltage while the magnetic field can be directly related to the current. In the case of electromagnetic waves, we are dealing with the transverse wave behavior. In other words, the electric field and magnetic field are orthogonal to each other. In other words, the plane in which electric field vibrates is orthogonal or perpendicular to the field in which magnetic field vibrates. And then also the vibration of electric field and magnetic field is perpendicular to the direction of the propagation. These are important properties of so-called transverse waves, and electromagnetic waves are a type of a transverse wave. What you see on this slide is a demonstration of transverse wave behavior in the case of electric and magnetic field or electromagnetic waves. So we see two planes, a plane in which we see vibration of the yellow arrows that would represent an electric field, and then also in horizontal plane you see the vibration of the blue arrows that represent the magnetic field. So in a XY plane we have a vibration of the electric field, while in the XZ plane we have a vibration of the magnetic field, and then the propagation is along the x-axis. In other words, the vibration of electric field, magnetic field, and direction of propagation are perpendicular to each other, and that's, as already mentioned, is an important characteristic of a transverse wave. Now that we introduced the electromagnetic waves, we also would like to take a step back and look at the entire electromagnetic wave spectrum. As already mentioned, light is a type of an electromagnetic wave that's visible to the human eye, but that's not the only electromagnetic wave that's present in the nature. Electromagnetic waves are spanning the whole range of frequencies from low frequencies of 60 Hertz, where we have our power grid, and then if you move frequencies to the kilohertz and megahertz range, we have radio and TV broadcast. If you are going to a 1 gigahertz range and above, up to 300 gigahertz, we are talking about a microwave spectrum, where we have a whole bunch of applications such as radars, satellite communications, wireless communications, etc. And then in the range of a terahertz, we have optical spectrum that consists of infrared spectrum, visible light spectrum, and ultraviolet spectrum. That's of all these three that make optical spectrum are of special interest for us in the photonics. And finally, if you go even higher in frequency, you're entering the range of X-ray rays, gamma rays, and cosmic rays. So this is a nice overview of the entire electromagnetic wave spectrum. In photonics, as I said, we are analyzing specific sub-region of so-called optical spectrum that consists of infrared spectrum, visible spectrum, and finally ultraviolet spectrum. This slide presents just a specific subsection of the entire electromagnetic wave spectrum. Namely, we are talking about the visible light. So, as already mentioned, light is a form of electromagnetic radiation, and it's basically consists of a whole bunch of frequencies that are represented as different colors, ranging from ultraviolet on one side and infrared on the other side. So the visible spectrum is basically starting with a purple or violet color, whose wavelengths are of about 400 nanometers and going all the way up to 700 nanometers, where we are in the range of red colors. So in the case of light, we are dealing with the waves that have very high frequencies or very small wavelengths. So we are considering light waves as being a very short type of waves. Their wavelength is usually expressed in terms of nanometers or micrometers. Specifically for the visible light, we are dealing with a range of 400 nanometers all the way up to 700 nanometers, representing all the colors of the visible spectrum. Very often in photonics, we are also going to use the different unit of length, so-called angstrom, where angstrom is equal to 10 to the negative 10 meters, so a relatively small unit that is also found its application in a field of photonics. This slide presents the visible spectrum in terms of the frequency. As it can be observed, we are dealing with very high frequencies of in a terahertz range. The human eye responds to the very narrow visible spectrum that is spanning the frequencies from 4.3 to about 7.5 times 10 to the 14 hertz. So this definitely is a terahertz range, or very, very high frequencies that represent electromagnetic waves that are visible to the human eye. An important property of light propagation or electromagnetic wave propagation is the fact that electromagnetic waves, or in this case light, is changing its speed of propagation if it's moving through different media. So the speed of light, as already defined, is equal to 3 times 10 to the 8 meters per second, and this constant can be applied only to the vacuum, or to a certain extent to air. If light propagates through different media like water or glass, the speed of light is going to be significantly reduced. And the way how we are quantifying this behavior of light is through a quantity called index of refraction. Index of refraction is a unitless quantity that is basically telling us by how much is speed of light reduced in a specific medium. So different media have different indexes of refraction, and again, the index of refraction is a measure of how much is the speed of light reduced in that specific medium. It also turns out that the wavelength of light is going to change in a similar way as the speed. In other words, the index of refraction is also going to be the factor that is going to tell us how much the wavelength of light is decreased in a specific medium. So as this slide presents, we on the bottom plot, we are seeing the light or electromagnetic wave propagating through the air, and we can see that when the light wave enters a different medium with an index of refraction n equal to 1.5, we see that the wavelength of the light has been decreased, and then also the speed of light is going to be reduced. So the fact that index of refraction is equal to 1.5 means that the wavelength of light is going to be reduced by 1.5 times compared to the wavelength of light in the air, and similar applies to the speed of light. So in other words, the speed of light in the medium whose index of refraction is equal to 1.5 is going to be reduced by 1.5 times compared to the speed of light in air. So to summarize, the index of refraction of a material represents the ratio of speed of light in a vacuum compared to the speed of light in that material. The index of refraction is always equal or greater than 1. It cannot be lower than 1. So index of refraction equal to 1 means that we are dealing with a vacuum, and for other materials index of refraction is going to be greater than 1. It's also important to note that the frequency of light does not change when the light enters a different medium. So the only two quantities that are changing their value as the light propagates from one medium into the other are the wavelength and the speed of light. So once more, the frequency of the light wave does not change as the light moves from one medium into the other.